Okay, for our last problem this semester, we're going to do a heating problem, okay? And so we're going to be looking at a heating. I've looked at air conditioning most of the time here. So let's look at heating. We're going to have a ductwork here. And we're going to have air coming in here at a temperature 1, which is equal to 15 degrees Celsius. And we're going to say that its relative humidity here is equal to 60%. Okay, so it's colder air. And we're going to run it over some heating coils. So heating coils. And we're also going to humidify that air a little bit. And we're going to say, all right, we want to humidify this air, and we're going to bring in, or we're going to inject water vapor. Okay, and we're going to say that this is going to come out here. So this is going to spray some water vapor into this system. And we're going to say that this is equal to the temperature 2 here, or actually we'll call this temperature 3 because we're going to have something here too. This is going to be state 1, state 2, state 3. Temperature 3, we're going to say that's going to be equal to 25 degrees Celsius, and our relative humidity goes up to be equal to 65%. Okay. And we also tell us, problem also tells us that right here at state 2, our temperature 2 is going to be equal to 20 degrees Celsius. So we know two things happen here. That the heating coils heats it up 5 degrees, and also the water vapor, that steam, also heats it up 5 degrees. It adds some water vapor to it to add some humidity. Now you might be saying, Dr. Michael, you told us long ago that we're going to be most comfortable at 65, at 45. This seems a little bit muggy air. Why would we want to humidify this air? And that's a good question. I just chose a problem. You might have a situation, industrial process. You have to have it a little bit more humid in your room than you would in other places. Okay, this is just the aspects of what this specific problem might be asking us for, and we can make that happen. If you're the engineer and they say make this happen, you can make this happen. Okay, they want us to figure out how much steam is added to the air. So they want us to find out here, A, what is the mass flow rate of my steam, and the second they want to say is amount of heat transfer to the air. So B, they want to find out what is my Q dot to that air. Okay. So if we look at the psychrometric chart, which I'm going to pause here and bring my psychrometric chart down so we can have another one here, we can start setting some states here, setting some properties. So I'm going to pause the video so I can bring that psychrometric chart down. Okay, here we go. I have the psychrometric chart brought it down. That'll be easier for us to work on. Let's say our first state is 15 degrees Celsius, 60% relative humidity. 15 degrees Celsius is right here. And then 60% relative humidity is going to be where it intersects with this line. 60% relative humidity, 15. This is right here. This is going to be my state 1. Okay. My state 2, or state 3, sorry, is going to be 25 degrees Celsius, 65% relative humidity. So we're going to go to 25, and then we're going to go to 65, which is about halfway between here. Here is going to be state 2. Okay. Now, how is it going to travel there? Well, we know that state 2, they told us state 2 is 20 degrees. And so state 2 is going to be 20 degrees, and it's actually going to be directly to the right of state 1. Why do we know that? Because no water vapor was added between state 1 and state 2. No water vapor is added. So this is going to be our state 1 to state 2. And then this is going to be state 3 up here, sorry. And then we're going to be humidifying and adding some heat transfer as we move up there to state 3. That's the path that we're going to be following. Now, in a higher level class that we're dealing with psychrometrics, we could find state 2 without having to be given that information. That's just how these problems will go. But this one gave us that information. It's a little bit easier, but it's still a challenge for us as we're still beginning to learn here. And we can find out what state 2 is and what state 3 is and kind of know how that path of how that works. And it makes sense to us. Okay. Let's see if we can find some values here. The enthalpy of our dry air. I'm going to say that HA plus omega HV1, I'm going to call that equal to 31. I don't know if I'll need it at state 2, but I'll go ahead and find it at state 2. HA plus omega HV2, I'm going to say that's equal to 2, 4, 6, 36. And then my state 3 I'm going to say that HA plus omega HV 3, let's say it is equal to 59. Okay, these are all going to be kilojoules per kilogram of air, kilojoules per kilogram of air, kilojoules per kilogram of air. That's what we're going to be working with. And we might need the humidity ratio. So let's look over here, humidity ratio. Our humidity ratio, omega 1 is equal to omega 2, which is equal to 0.007. And for 3, that's going to say that's equal to 0.013. Okay, this is going to be in kilograms of water all over kilograms of air. Kilograms of water vapor all over kilograms of air. Okay, so that's what our psychrometric chart told us, and that's what we will work with here. Now, the question that we might ask ourselves is how much water vapor was added to the air? Okay, so we can just subtract these two. We could say, well, the change in omega is going to be equal to 0.013 minus 0.007. And so if we do that, we're going to get 0.006 kilograms of vapor all over kilograms of air. So we have there. And so let's go and start working on the rest of our problem, what we'll need for the rest of our problem. Okay. If I go here and I find out, I haven't been given a mass flow rate here of my problem statement, so actually that's all I need there. If I know how many kilograms of air is being added, so I'm going to have to figure out this problem here did not tell me what the mass flow rate of my air is. They're just asking me how much humidity would be added per anything. So let's just say I was going in with, I don't know, 10, I was doing this at 10 kilograms of air per second. Okay, then that gives me basically 0.06 kilograms of vapor are added per second. Okay, so putting it in terms per kilogram of air is a kind of nice way to do it, because then I can scale it depending on how much air is coming into the system. So it's pretty straightforward and easy there that we're working with. Okay, so that answers our first question we had here was what is the mass flow rate of my steam? Well, the mass flow rate of my steam has to be the same as the change of water, change of humidity ratio. I have to add 0.006 or 0.006 kilograms of vapor for every kilogram of air. And how am I going to add that? By injecting 0.006 kilograms of steam for every kilogram of air that we add there. Okay, that's a fundamental idea we have to make sure we understand. I hope that you can understand that, and that calculation is very easy using the psychrometric chart. Okay, now let's talk about what the heat transfer is going to be. So if we go here, if we go dE dt is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in minus the summation of my mass flow rates exiting times my enthalpy exiting. And we want to look at the whole thing. This whole thing is my control volume that I'm going to be analyzing here. Let me change my pen here. This is the whole thing I'm going to be analyzing. I want to look at this whole shebang. Okay? And so I got rid of kinetic and potential energy. I'm going to say it's steady state. I'm going to say there's no power. So I'm going to get 0 is equal to Q dot plus the mass flow rate of air times the enthalpy of air at 1 plus the mass flow rate of my vapor times the enthalpy of my vapor at 1 minus the mass flow rate of my air times the enthalpy of my air at 3 plus, minus the mass flow rate of my vapor times the enthalpy of my vapor at 3. Okay, and again, I know that the mass flow rate of air is going to be constant there, so I'm going to take this out. Q dot plus the mass flow rate of air times HA1 plus omega 1 HV1 minus HA3 plus omega 3 times HV3. Okay, which happens to be those mixture enthalpies that we just looked up for 1 and for 3. Okay, we looked up for 1, we said that was equal to 31. This is equal to 31 kilojoules per kilogram of air. And this one is equal to 59. 59 kilojoules per kilogram of air. Okay, so if I want to figure out my Q dot per my mass flow rate of air, this is going to give me a value of 59 minus 31. And 59 minus 31, 59 minus 31 is equal to 2.8, 28 kilojoules per kilogram of air. That seems high. That seems high. Let me see if I can find out. Well, that's a total because we're adding something with our steam. Okay, so how much of that would just be from our coils? Let's just find out how much that would be from our coils. For our coils, if we did that, we would still have 31, and our second reading is 36. 36. So 36 minus 31, we're just adding 5 kilojoules per kilogram of air from our heating coils. So the majority of the heat that's being added to our system is coming from that steam, that really, really hot steam that's being added in there, and to figure out what's going on. Now we could, if we wanted to, we could calculate, well, what's the temperature of that steam that is put in there. We'd have to find out how much, what temperature would help us provide 23 kilojoules per kilogram. And we could do that. And that's a little bit more than what I want to do right now. What I basically want you to understand is how we take these equations and put them into these nice and easy forms, and how we use the psychrometric chart to get values that we can really easily put into our equations. Okay. So today, what I've done is I've done a very difficult problem in that cooling tower, and then I've done a relatively easy problem here with this heating problem that we're dealing with. And on your exam, you're going to have to deal with probably a duct that's going to have either a heating and cooling section. It's going to have dehumidification and humidification. It's going to be, can you take this equation here? Can you simplify it into the terms that we can get things from the psychrometric chart? Can you look up those values in the psychrometric chart and plug them in and understand what's going on here? Does it make sense to you? If this psychrometric chart doesn't make sense to you, if you can't see where we're adding and removing water vapor, if you can't see where we're heating and cooling on there, you need to spend some time on it, because this problem should be a good chance for you to get a lots of 25 points. It's not supposed to be the most challenging problem on there. As long as you're in the right mindset, it should be okay. But if you're not, it could eat your lunch, and I don't want that to happen. Okay? With that, we have ended today, and we have ended the summer, and I want to thank all of you for your patience and your perseverance here this summer as you spent time in my playroom listening to me lecture to you. It's been a challenging semester for me. It's been a challenging semester for you without everything that's going on. But I hope you learned a little bit of thermodynamics. I hope you were challenged a little bit. I hope that you understand the lovely science that it is. Some of you may have said, I never would have seen a thermo equation in my life. I understand that. But I hope some of you are compelled to take Thermo 2. This summer semester is a very accelerated semester. It's for some people that really works. For some others of you that leaves you a little bit behind. But I'm hoping that you gain some appreciation of this class. And I'm sad that I didn't get to meet you in person and see your beautiful faces in my classroom. But I do want to stress again that in the things that you're going to see to give evaluations from me in the T-Val and in just the feedback that you're going to have, T-Val is completely anonymous. You can rip me a new one. You can say, man, Wanklyn didn't know what he was doing. You can say whatever you want to on that. The other questions are going to be non-anonymous. They're going to be tied to you so you can get your extra credit points. I'm going to ask you, how could I make my lectures better? How could I have done different things with lecture quizzes? What would you like to see in an online class? Because this is really my first online class that I've taught in my 10-year career. And so I'm basing a little bit on what I learned from last spring, but I'm also interested in learning what I can learn from you. And don't be afraid to be critical. Also, don't be afraid to say some things that you enjoy about it. Like I said, I am a human being. I want to hear the rainbows and butterflies as well as the things I can work on, and I will take that in my future as I work on that in the fall semester, because I'm guessing we're going to have some more online learning unless magic occurs and this coronavirus nonsense disappears from the face of the earth. So with that, I want to thank you once again, and I want to wish you well. And I will see you Friday at 7 o'clock p.m. For our final time together. See you then.